Hey guys, welcome back to another video. So here we'll be going through the last two questions of the paper C1, okay? And I had a quick look at them, and I'll be honest, they're not as bad as the previous years, so let's go ahead and do this. So let's start with number 14, okay? So figure 2 shows a sketch of the curve C1 with equation y equals fx, where fx is defined by this. So it's a mixture of a quadratic times a linear, so this ultimately makes a cubic. And looking at the shape of this is a cubic graph, okay, where it cuts at minus half and it bounces off 2, so meaning there's a repeated root, so there's 2 roots here. That's why they squared this bracket, okay. And you also got a turning point which occurs at point P, and again this is also known as a turning point here. So when you have a turning point, we usually find the coordinates by using a gradient equation. We usually use differentiation, where we set dy over dx to 0. When you solve this equation, you find the value x. One of them is obviously going to give you a 2, and the other one will give you another x value to find p. But anyway, let's go ahead and look at part A now. Okay, so there is a maximum turning point at the point marked P. A. Use the first derivative of fx to find the exact coordinates of the turning point P. Okay, straightforward. So literally walking you through here. So here's our fx function. So what you should do is actually expand this first. So let's go ahead and expand it, yeah? So I'm going to rewrite this one as fx equals x minus 2, because there's 2 of them, x minus 2 and then 2x plus 1. I'm going to go ahead and open up the right two brackets first, yeah? So you got x minus 2. So you got x times 2x is 2x squared. X times 1 is 1x. Minus 2 times 2x is minus 4x. Combining is minus 3x. Minus 2 and 1 makes minus 2. Now, I'm going to open up the first with the second again. So I'm going to times everything here by the first term, which is x. So x times everything will give us 2x cubed minus 3x squared minus 2x. And now I'm going to times again everything over here by minus 2. So you can get minus 4x squared plus 6x plus 4. A little key note, guys, yeah, when you want to expand a quadratic with what's it called, linear, it's good to line up the powers, yeah, because this just makes it easy to collect. So now collecting things, yeah, we got 2x cubed on its own, minus 3 minus 4 is minus 7x squared, minus 2 and 6 is plus 4x, I'll delete after, and plus 4. So here's our equation now, yeah. So therefore, just making it clear over here, we're left with fx equals 2x cubed minus 7x squared plus 4x plus 4. Okay, so now just reviewing the question, they want us to find the first derivative of fx, yep. So doing so, by the way, this is the same as dy dx, yeah. And this is also known as, again, the gradient equation, which is what we need to find the gradient and the turning points. So differentiating this, the rule is that you drop the power and subtract by 1. So dropping 3 down, 3 times 2 is 6, subtracting the power by 1 is 2, rinse and repeat. And if you left it just an x, it vanishes. If you got a constant, that whole thing goes. So that's done. Now, to actually solve this, it says here, and the note I put over here was that the gradient equation is set to 0. When you solve this equation, this means that the gradient is flat. When it's flat, it's we set it to 0. So we have to set this equation to 0 and solve this quadratic. Now this is easy. You just use the quadratic formula. So I'm going to lay out for you guys. So the quadratic formula is x equals minus b plus minus square root of b squared minus 4ac all over 2a, where, according to our quadratic above, a equals 6, b equals minus 14, and c equals plus 4. Right, so again, when you put this into the quadratic formula, always wrap the letters in a bracket. So minus 14 here would be minus 14, or bracket. Well, it becomes positive here, and so on. So when you guys carefully do it, you should get 2 results. One of them being a third, or one of them being 2. Now, as expected, one of the solutions has to be 2, because according to the graph, you have 2 turning points, and one of them is 2. So that's correct, meaning this one must be a third. So x over here cuts at a third, yep. So we found the x coordinate of P. How to get the y coordinate? Well, you can plug this into any equation which describes this curve, and the curve is described by this equation here. So replacing all the x values with a third, we're going to get a third minus 2 all squared, and 2 times the third plus 1. Putting this in your calculator, and you should get a final result of so point P would be a third, comma 125 by 27. And that's it, guys. You're done. And this is, in my opinion, in easy 7 marks. Okay, this is easy marks to bag. Okay, part B. So before part B, a second curve C2 has the equation y equals fx plus 1, where now x has been replaced with x plus 1. Okay, so what that actually means is that you literally replace these x values with x plus 1. And what it means graphically, if it's a plus something in the bracket, this means you shift all the x values by 1 to the left. So in other words, it's going in this direction. It sounds weird. You'd think it moves to the right because it's positive, but what that means is that everything is shifted in reverse. Okay, if it was x minus 1, then you shift it to the right, so the values of x move along this way. So 2 would become 3, minus half it becomes plus half, and so on. I should really tidy this up a bit. Okay, so let's go ahead and solve part B. So write down an equation of the curve C2. You may leave your equation in factorized form. That's really kind of them. So what we're going to do, replace this x with x plus 1, yeah? So we can say this one is equal to, bracket, replaces with x plus 1, so you got x plus 1, and then, of course, minus 2 squared. Now this one is 2x, so replace that with 2, a little bracket, x plus 1 plus 1. Now all you want to do, guys, is literally just tidy up the inside, yeah? So this will be tidied up 2, so 1 minus 2 is just, minus 1, so x minus 1 squared. So expanding this carefully, you got 2x plus 2 add 1, so it's 2x plus 3. Okay, and that checks out. C. Use your answer to part B to find the coordinates of the point where C2 meets the y-axis. Okay, so when let's have a look. So when C2 meets the y-axis, and that's actually, you don't even need a graph for this. When something meets one of the axes, this means that the other coordinate is 0. So if you meet the y, this implies x coordinate must be 0, because that's the only way for it to hit some curve, hit the y-axis. X should be at the origin. So when x equals 0, you just plug into this equation here. So you're going to get y equals 0 minus 1 squared, and then 2 times 0, which is 0 plus 3. So this is your final result. So putting this in the calculator, you should get a y coordinate of 3. So therefore, the coordinates of the points where curve C2 meets the y-axis is just simply x is 0 and y is 3. Oof, this question is quite chill, isn't it? So next one, D. Write down the coordinates of the 2 turning points of curve C. Oof, literally the same as this one, yeah? But we just explained that the curve, because it's x plus 1, it shifts to the left by 1. So this coordinate point, because it was 2, it shifts, you subtract 1, so it shifts to 1. So we've done one of them. So actually, let's put it here for a second, yeah? So this was our previous points. And by the way, the other one over here, 2, this was 2, 0, because again, it hits the x-axis and it hasn't gone up or down. So our 2 turning points was 2, 0. Let's call this M for max, yeah? This now, so for part D, the M coordinate now becomes 1, 0, because it shifts to the left by 1. And P now becomes, so they give him a little dash. So a third, subtract that by 1 gives you minus, mental maths, 2/3. And again, the y coordinates don't change because you ain't shifting the y, you're shifting the x. And that's all. That's this part done. Yep, so y is the same, x is that. Let's go back to the last bit now. So E. Sketch the curve C2. With the equation that, so basically sketch that C2 that we've been working on, given the coordinates of the points where the curve crosses or touches the x-axis. Notice how they don't care about the y-axis here, yeah? So you don't even need to worry where it hits the y, but that's not too hard to find. So for the sake of convenience, yeah, we're going to go ahead and try and sketch it and see how it looks compared to the old graph. It's better to draw on the same graph and then update also. For you guys, oh great, PC and battery saver mode. No worries. So everything shifts to the left by 1, so minus a half. Over here becomes minus 3/2 because that's what happens when you take away 1. 2 here is now at 1, and a p coordinate here, so what was the p value? It was a third. It now goes to the left at minus 2/3, which is around here. It's less than minus a half, by the way, yeah? So the graph is now going to look something like, hold on, change color pen. Here, hits at P, the new P here, and then dips down to 1 here, and then shifts upwards. So that's it. This would be your y equals fx plus 1. Now, just to be clear, you don't do on the same graph. You're going to probably draw it, where is the graph? So you probably draw it, yeah, you'll draw it around here. Okay? But anyway, guys, that's it. That's 14 done. I hope this helped, and I'll see you guys at number 15. Okay, number 15. So a design for a logo consists of two finite regions, R1 here and R2 there, shown above. The region R1 is bounded by a straight line L and a curve C. The region R2 is bounded by the straight line L and curve C with equation x equals 5. So you got a third line up here, yep. The line L1 has this and curve C has that. Cool. Given that the line L meets the curve C at points, what's that, minus 222 and 470, use integration to find, I love how they tell me to do, the area of the larger low region and the exact value of the total area. Alright, cool. Let's try our best. So we'll start with A. Now, one thing to note here, yeah? So we read everything. The only way to calculate this region 1 is to think about what kind of shape we've got here. Well, when you use integration, the purpose of integration is that it calculates area under the curve. So we can see we've got a curve here, yeah? So if we just draw a dotted line here for a second, yeah, to see how long the curve extends. So just draw a straight line going down from the 2 points. So this point here is just minus 2, and this point here is 4. Calculating the area under the curve will calculate this white region here, all the way up to here, yep. So that's the area we would find. Let's just give this a name for a second, yeah? So this area here is going to be called I1, yeah, and just I. So the integrating area. Now, another thing we can also see is that this shape, which covers from minus 2 to plus 4, you can see some sort of trapezium shape, yeah? So a trapezium is formed. So let me just line that up. So we got from here to here, all the way across here, and following this line. So here's a trapezium where we got two parallel lengths. So these are parallel lengths of, look at the y-axis from 0 to 22. So it's 22, length of 70, and we got a width now from minus 2 to 4 of 6. So effectively, the way to calculate the region 1, so if we had to do like a formula, we could say that the region 1 is composed of finding the difference from the area of the trapezium and the purple region, which I called I1. So that's it, guys. If you can work out this equation here, you found area, you found the region 1. So let's start with the easy one. What is the area of the trapezium? So we could say that area of trapezium AT is literally the average between the two parallel lengths. So the average, which is half of, between 22 and 70, 22 plus 70. So this is the average between the two lengths times the other length, so the perpendicular length, so the width, which is 6. Okay, so that's one thing. Doing this in your calculator, you should get 276. So that's the area of the whole shape, the whole trapezium. Now, as for the purple region, the I1, well, we need to use integration and calculate the limits between minus 2 and 4. So let's do it here. So for part A, we can call this I1. We want to integrate from the two bounded limits from minus 2 and 4 of the curve, okay, with respect to x. Now the curve, we know the formula is for the curve. It's right here. So 4x squared plus 6. So what we do, we just update this curve equation, right? 4x squared plus 6 dx. I use a bracket here because it's just to indicate that you're integrating all of this respect to x. Okay. Now integrating this one is not too bad. The rule is that you firstly just increase the power by 1, so it'll be 4x cubed and divided by its power. Same. If there's just a constant, you just do 6 and stick an x in. Okay. And because you've got limits, put some nice square brackets and put minus 2 and 4 here. So this implies that you can replace the x values firstly with 4, find a solution that then replace it with minus 2, and then find the difference. So ultimately, replacing the x values of 4 in your calculator, you should get something like 328 by 3. and then subtract, and then replacing what's it called, the x values of -2, you should get -68/3. And then just computing this, which isn't too bad, okay, it's not, approximately is equal, you should get 132. Now that kind of looks legit, because if you look at the values, we got 276 for the whole trapezium, and to be honest, this region, I don't know which side is actually bigger, but as long as your I1 is, as long as your area under the curve is smaller than your actual trapezium, then it looks alright. So now we can say, alright, so therefore R1 must be the difference between 276 and 132. So just write it down to show you guys. 276 minus 132. Calculating this, and you should get 144 units squared. It's good to give it a name, yeah? And now for part B, we're going to need to find the exact value of the total area of the two shaded regions. So R1 plus R2. Well, we got R1. Let's try and work out R2 then. So looking at R2 carefully, it's kind of similar actually to R1. It's more or less the same thing. The only difference now is that the limits are between 4 and this new line 5. So x equals 5. So far, what kind of shape do we have here? Well, we can see that the curve is flowing from here, yeah? So here's the curve. So when you use integration, you'll find the area under the curve. So it's going to cover the whole region. And now the trapezium is actually here. This is the trapezium. Okay? We have a trapezium here, and we got the area under the curve from the red line downwards. So, now the only problem here is that we're actually missing some information. So let me just delete this part for a second, yeah? We've got a height here. Actually, let me delete the green as well. So we know from the left side of the orange line, there's a height of 70 because it goes up 70. But what is the height of this line? Well, we know that first things first, that this line equation here has an x coordinate of 5 at this point here. So all we do is substitute the value of x equals 5 into that line equation here. This will give us the exact coordinate of this point right here. And once we have the exact coordinate, we can see the actual height of it. So go on. So replacing x with 5 here, if you put x into x equals 5 into this equation, you should come out of a y coordinate of 78. Okay, so that checks out. So this implies that this coordinate here is 5,78, meaning we have a height now of 78 from here to the bottom. So working out the area of trapezium is easy. Okay, so let's just delete this as well. Delete that, delete this. You don't need this anymore. So trapezium, so let's define a formula. We can say to work out the area of R2, the region 2, it's going to be a difference from the whole integration. So let's call this I2, which implies that this is the area under the curve using integration, minus that little trapezium area. Okay, so trapezium, we already worked out 80, which is going to be the average between the two parallel sides, so 70 plus 78 times the width. Well, the width is just 1 between 5 and 4, so times by 1. So that's no different. Putting this in your calculator, you should get 74. So the area of trapezium is done. Now all we need to do is work out the area under the curve between 4 and 5. And that's it. So let's do it here. So it's actually going to be similar to part A, in fact. So actually, yeah, so there's not much new things here, is there? So I2 equals the integral from 5 to 4 this time of the same thing as above. So I don't even know why I'm copying this down. It's actually the same. Result is obviously going to be the same. 4x cubed over 4 plus 6x. Difference is the limits, 4 to 5. Well, we know what the result at 0.4 because we just calculated it. It was 328 over 3. Now, but at 0.5, so we do 5 first, replacing x values of 5, you're going to get firstly a result of 590 over 3 minus the result at x equals 4, which was 328 by 3. Okay, so this is just easy subtraction. It reduces to 262 by 3. And now we found I2. So going back to the formula, we said that the region 2 is the difference between I2 and AT. So it'll be 262 over 3 minus 74. So region 2 equals was it 262 over 3 minus 74? That'll give us 40 over 3. Quite small. Yep, makes sense. And that's a small area. So that's it. We found the region 2. So So therefore, part B, the exact value of the total area of the two shaded regions. So it'd be R1 plus R2, R1 plus R2, which is going to equal now. So in your calculator, write this down. 40 over 3, which is over here, plus 144. So 144 plus 40 over 3, and it comes down to 472 by 3. Or if you want to write a mixed number, which is not even important, 157 and 1/3. And that's it. And that's, again, units squared. Now the last one is easy, you know, it's too easy. So given that the area of R1, which we have, is 144 over the area R2, so 144 over the area R2, which is 40 by 3, equals K. Find K. Trust me, they didn't even try at this stage. So you just divide these numbers, and well, I got the mark scheme up and I can't bother to figure it out. The answer is 10.8. And that's it. Question done. So this is 10.8. Anyway, guys, I hope this video helped. Let me know if you got any questions, and other than that, if you guys enjoyed the video, please give me a like, subscribe, and especially share to your friends, you know, because the more my channel gets exposure, the more I can produce good content, and the more that YouTube will help fund my projects as well. And this will help me produce better videos, more past solutions, everything, you guys name it. Anyway, guys, have a nice day, and I'll chat to you guys soon.